Welcome back to my channel. I first saw this problem floating around on YouTube, and the solution people usually show is more algebraic. I do plan to summarize two algebraic routes in a later video, so if that interests you, subscribe now so you do not miss those follow-ups. But in this video, I want to do something older and more visual. I want to show you how Euclid, around 300 BC, would look at this picture by synthesis, by auxiliary lines, and by moving equal pieces around the diagram itself. A picture like this usually admits many synthetic approaches, not just one. Once you start seeing parallel shifts, congruent triangles, and equal diagonals, the figure becomes generous. So what you are watching here is not the synthetic proof. It is one synthetic proof, chosen because the moving construction makes the logic especially easy to feel. The big structural clue is that almost every useful angle in this picture is either 45 degrees or 90 degrees. That means equal legs keep generating equal hypotenuses. Diagonals of squares keep behaving rigidly, and little corner triangles keep echoing one another. Once you notice that, relationships become abundant. The diagram is practically asking for a synthetic argument. Here comes the first auxiliary move. Extend the long tilted side across the square until it meets the boundary at two new points, one on the bottom edge and one on the right edge. This is classic synthesis. Do not calculate first, enlarge the figure first. The extension creates room, and that extra room is where the hidden equal lengths will soon reveal themselves. Now we name the obvious pieces. The larger corner gaps are called x, and the smaller corner gaps are called x prime. These are just convenient labels. They are not mysterious variables hiding some heavy computation. They simply split a side of the unit square into two complementary parts, so whenever you see one of them, the other is already nearby in the same edge decomposition. This is where the 45-degree structure starts paying rent. The moment one little segment is identified as x prime, matching right isosceles pieces start forcing other segments to share that same length. So we are not solving for x yet. We are propagating equal lengths across the construction until the whole picture speaks one common language. And the echo repeats at the top of the figure. Nothing essentially new is being assumed here. The same right angle, the same 45-degree slant, and the same isosceles logic are simply reappearing in a new location. That is one of the pleasures of synthetic geometry. Once the picture locks into a pattern, the same idea keeps playing out in different corners. Now the diagonal becomes the hinge of the proof. Where it meets the extended tilted side, the construction produces one more pair of matching pieces. At this point, the diagram is dense with equal lengths, but the logic is still purely visual. Right angles, 45-degree turns, and equal pieces transported from one corner to another. This is the heart of the synthetic argument. Watch the pieces rotate and flip into alignment. Nothing numerical is happening here. We are simply transporting already known equal lengths into a new arrangement until two congruent corner constructions become obvious to the eye. Once those matches are visible, the outer square starts giving us fixed whole lengths, not just small repeated pieces, and the proof suddenly has real leverage. Once the congruent pieces are in place, one final synthetic move becomes natural. Take the diagonal of the unit square and slide it across in parallel. Because parallel translation preserves length, the diagonal carries its full length with it and lands directly on the extended tilted segment. That is the decisive geometric replacement. A familiar whole length from the square is now living inside the auxiliary line we created at the start. And here the construction closes. The full extended segment is fixed by the outer square. One visible portion is exactly the shifted diagonal. The remaining visible portion is exactly x. So x is not discovered by grinding through equations. It is identified as the leftover piece after a chain of synthetic equalities has reassembled the whole line in front of us. That is why this proof feels Euclidean. The answer appears as a remainder of a construction, not as the output of algebra. So that is one synthetic solution, and I think it is the most satisfying one to watch. The picture is full of more roots than this, and the more algebraic solutions are worth comparing too, which is why I will return to them in a later video. If you want those follow ups, stay tuned and subscribe. For today, the main takeaway is simple: auxiliary lines plus rigid angle structure were enough. No heavy algebra, just synthetic geometry.